Hello everyone, I'm Kostas and I'm going to present HashWires, a purely hash-based rain-proof system applicable in settings for which there is a trusted third party that issues commitments over credentials. I go by Kostas, by the way, and this is a joint work with Sir, Kevin, Frederick, and Yolan. We will start with the simplest application of HashWires, which is proving that you are older than some threshold. And we will do that by basing our solution on top of Rivers and Samir proposal in 1996. And we gradually apply modifications to make the ON like efficiency to log n. We achieve this by introducing the minimum dominating partition algorithm and also some hash-based accumulators on top of the scheme. Regarding application, we will see some real-world cases of HashWires and compare it against zero-knowledge proof schemes such as bulletproof and 1216. So let's go back to the age proof example, and let's assume that Alice wants to prove to a grocery store that she's older than 18. On the left side, we have the government who is issuing a commitment over Alice's age by just picking a random value R. And then Alice is able actually to prove for any threshold that she is older than this. And this will succeed only if the threshold is less than or equal to X. Obviously, the verifier should not learn anything else except for that statement. So how do we encode this in hash chains? It's very easy, and let's focus on the right side where we have this hash chain here. As we know, the issuer knows the value R, and then they can easily create this hash chain like by successive hash invocations until they reach h to the x of R. This means that the latest element is the commitment. And how does this help? It helps because by convention, we feel that the commitment is correct under some value because the length of the chain is actually the real value you're encoding. And now Alice, who also has access to the R value, she can compute like the chain up to the h x minus t, and then provide this as a proof to Bob. And what Bob will do, Bob will again continue to hash this proof until he reaches the commitment. And he's like 100% sure that Alice had a long enough chain, which is at least 18, which means that Alice is definitely 18 years old or more. As you can see, there is a commitment conditional soundness here and the witness indistinguishability because Bob learns nothing else about Alice's age. However, it's not a real zero-knowledge proof scheme because there is some leak which doesn't affect our application, but in the strict zero-knowledge proof like terms, the verifier learns the pre-match of the commitment. Also, you have to realize that in our particular case, the verifier does not provide any random challenges, nor do we use any fiat Samir transformation as other zero-knowledge proof schemes. Another major problem with this solution, however, is the fact that it doesn't scale. Imagine if we were in the domain of billions or 64 bits. I mean, you cannot have so long chains, right? I mean, it's impractical. So how do we solve this? Our first attempt was actually to actually create a commitment over some value and split it by digit. And by digit, in this particular case, we mean that we have the commitment over the value 033039999. And let's assume that the max number is 5 nines, 999999. We can prove a number. I mean, if we do it per digit, like for 0, we have like only one element. For 3, we have like 0, 1, 2, 3 elements, like 4 elements in total. For 9, we have 10 elements and so on. And this actually can help us actually prove the number 1492. Because if you want to provide the proof for 01492, you provide the first element here. Bob will hash it 0 times, so it uses directly this. We have the number 1 here, and then you will hash it once. You have the number 4 here, you will hash it 4 times, and then 9 times, and then 2 times. Then all of these 5 commitments, now we have 5 commitments instead of 1, is actually a proof that an evidence that Alice has a value, a credential of at least 1492. And obviously, in real world, we can just combine all of these commitments into one by just concatenating them and hashing them. However, as you will see, this is not like a full solution. And the reason for this is if the number was different, like the 03997 here, we would have some difficulties on like proving numbers which end to 8 or 9. As you can see here, you cannot prove 1599 because the last chain is not enough to actually encode 8 or 9. Like it's very short here. So this attempt actually cannot work, and then we had to go to something else. So in our particular case, what we did for like HashWires is we actually explored the minimum dominating partitions theory, and we tried to identify what are the potential, let's say, ways to split the number without having the problem we mentioned before. We ended up like into a solution where a number X dominates another number Y if all of its digits are equal or larger against the corresponding digit position of the other number. As an example, imagine that 2, 3, 4, 5 dominates 1, 2, 3, 4, because 2 dominates 1, 3 dominates 2, 4 dominates 3, and 5 dominates 4. So per position, we have like the first number to dominate the second one. So if we apply this, we can actually create splits of different numbers. And for example, the number 399 is by itself enough to encode any number smaller than this, like 3999 can encode any number below it. But what if we have 3413? Then we can introduce new partitions to this algorithm. And in this particular case, is these four numbers here. And the reason that this works is because imagine that the last one can actually encode any number below 2999. This number here, the 3399, can encode anything above this one, but until this one, this number. And then this number can encode anything above this number, 3399, so 3400, until 3409. And this one can encode any number from 3410 to 3413. So in practice, with these four partitions, we know how to encode any number below it. And because we don't have a bigger number, we cannot encode a bigger number than what we were issued. The same is for different bases. For example, for 312, this is the minimum dominating partition. The counter example is, for example, is if in 4313 we missed the 349, the numbers between 3400 and 3409 are not dominated. So this is not an MDP. And you will see, I mean, you can easily understand that the MDP algorithm actually ensures that the maximum size of this list can actually be as many digits as the number is on this base. And you can even identify like how easy it is to compute it. I remember we had some original comments from the reviewers. Oh, we don't know how effective it is to actually create the MDP. And we saw here, and we implemented that as well, that it's super fast. It's just a for loop over a number of digits times. And whatever you can read better, like code or the algorithm itself, it's like it's not reducing any efficiency issues in our algorithm. It's super fast. So we can go actually on using this MDP to actually convert it to hash chains, right? So from the MDP values, the values themselves are not enough, right? We just need to actually convert them into this particular construction. And what we do here is we separate them, and for each particular number, we create a chain. So this is 312. Obviously, we have for 0, 1, 2, 3, for 0, 1, and for 0, 1, 2. So for 303, you have like 4 elements here, 0 here, and 4 elements here. And you do the same for 233. What's the trick here? The trick is HashWires is like a one-time witness in this distributability scheme, where Alice can actually, if she receives all of these three commitments, she can actually pick which one to actually use every single time she's requested to provide the proof. And that's the benefit, because here, if Alice is requested to provide the proof for 1, 2, 3, she will go on the right side because this one can encode any number below 2, 3, 3. And she can provide like the yellow node as a proof. And this is true because this yellow node can prove 1, 0, 1. This node can actually be hashed twice by Bob, so 0, 1, 2. So Bob is sure that you have at least 2 here, and Bob is sure that you have at least 3 here. So you have 1, 2, 3. If the issuer doesn't give you any other number, Alice cannot prove any number larger than 3, 1, 2. However, as you can see, previously we had like different hash chains based on the different MDPs. And if you have a lot of MDPs, you're introducing like some complexity to the system because you need to implement like many hash chains, which is the most expensive operation. One way to do this is because it's one time again, we can actually create just 3 elements here for 3, 1, 2 in base 4, and actually wire them efficiently. And you can see in the next slide why the wiring is super simple. Imagine previously they were completely independent, but what we do is we actually create 3 hash chains, and then again we keep the positions similar to the previous one. So here we had like a wire to the 3rd node from the 1st chain on the left. Again, as you can see, it's on the 3rd node, 0, 1, 2, 3. Then it was like on the 2nd node, again, the 2nd red goes to the 2nd node here. And then we have like a link to the 1, 2, 3, and then as you can see, the third one goes to 1, 2, 3. The same applies to all of them. So in practice, instead of having 9 chains, now you're using 3 chains, and then with smart wiring, you know where to go. Also, one of the problems of these applications is if you reveal the number of MDPs, you're actually leaking something, and we don't want it. That's why, on top of the MDPs that we had before, we're actually introducing some Merkle trees, and the commitments to different MDP values are actually nodes on this sparse Merkle tree here. And we also sample them, so you don't even know if you have one or this was the second MDP value. So no leaks by assuming that this could be a full tree or it could be a tree with one node. You don't know because every single time the verifier will receive one path. And then eventually we end up into a system which looks like this one, which is like, imagine a full version of HashWires. And in this particular case, you can see like the merging of the hash chains on the bottom. And then we have some accumulators here to actually compress the 3, let's say, commitments into one, and then we put them in a shuffler, and then the shuffler actually goes into a Merkle tree to produce the root. And we also have some malleability, like this is optional. If you don't want someone to use your proof and prove another proof with your proof, like a smaller proof with your proof, then you can introduce a non-malleability like chain, similarly to how hash-based signatures are doing. I will go back to the applications, which is one of the most interesting things about HashWires. And what we have here is you can use HashWires for KYC proofs. In our particular case, we had AIDS, but in practice, it can be any numeric key KYC information. Something which is also interesting is the proof of income. Imagine that we might go to landlords. This was very important when we did some survey on the use of like HashWires. And the landlords will require like evidence of your salary or evidence of your income. Imagine that now people who don't want to reveal everything, they just want to prove that they meet the threshold. And this is enough actually to convince them. And because the algorithm is very simple, it just has functions, it can even implement it, I don't know, in the identity cards or some smart cards internally, even in the blockchain, because you don't even need like functionality of bulletproof or other verification systems. Usually the hash function is available on most of the blockchains like Ethereum and Diem and so on. Another interesting application that we figured out is the proof of valid timestamp. There are a lot of attacks happening because the malicious users can a priori see the expiration time of the certificate and they can prepare the attack. So there are even bots about this. What if you don't know when a certificate expires, right? And you only know that at the time you're entering a web page, an HTTPS page, it's valid now, but you don't know when it expires. Another interesting stuff is the location privacy, where this one actually introduces a new concept of overlaying like HashWire proofs. In this particular case, we have like the x-axis being a HashWires proof, the y-axis also being another HashWires proof. And then because you have ranges, you can create rectangles now, and you can prove like you're located somewhere here in Iceland, like you have your address in your identity card, but you don't reveal exactly what your address is. I only know you are in this rectangle now. And with introducing like different points of reference, we can even create different shapes. It's not only rectangles. You can make like hexagons and other stuff. Another interesting application is micropayments and backchecks. Imagine that if we want to have like some, especially in the blockchain, some checks where you cannot see the real value of the check, but you gradually redeem it. So you can start like by issuing a bank check of 1,000, and then you go on the blockchain and you spend like 100 of them. Nobody knows you have another 900 on this check, but they know this 100 was actually at least issued by the bank. And you have more and you have more, and at least it expires. You don't have enough money anymore in your check. Another interesting application is policy-based signatures. And this is very important because we actually realized with HashWires that almost all of the hash-based schemes, at least the few times or one-time hash-based schemes like WATS, BPQS, and Lamport, can actually be converted very easily to policy-based signatures. And imagine in Bitcoin, what does this mean? For this particular policy, by the way. So there might be an owner of the key. This owner of the key sending the key to some other nodes, some other users. but by putting restrictions on what you can sign. Like I'm not giving you the full chains, the full what chains. I'm giving you only parts of them. So you can sign up to some amount in Bitcoins. Finally, there is some interesting like applications in proof of ranking, like for games or for your CVs. You might not want to reveal that you were fourth in your school, but you want to prove that you were, I don't know, in the top 10, right? The same thing for like a chess game or something. And there is also the, I mean, in the food industry or the drug industry for secret recipes, right? Imagine that you want to prove that you meet the regulations, but you don't want to reveal all of your recipes, not everything, right? And finally, we have to mention, because this is a question that we usually get, HashWire commitments are not homomorphic, which means that we cannot use them like Nibble, Wimble, or other schemes that require like adding commitments between themselves. Unfortunately, this is a limitation of HashWire, one of the limitations of HashWire. Finally, we go to the comparison efficiency, and we're super excited here because we have some record like numbers, especially for like 32-bit integers, for example. Imagine that we can produce with 2048 long chains, which is still super feasible and super fast. You can actually produce like signatures of 177 bytes, which is even smaller than gross 16, right, which is 192. And in practice, if we can relax the collision resistance, if we trust the issuer, it can even be smaller because we don't need 256-bit output. So another benefit is actually on the speed, because we're implementing this in Rust, and then we have a great implementation of bulletproofs, even with vectorized instructions, AVX2. And we realized that HashWires is a lot faster, especially on proof generation. Imagine that something that takes like 12 milliseconds for bulletproofs, it actually takes 100 microseconds in HashWires with basic thing like length of chain is like up to 16. Obviously, the comparison is a bit unfair because these are generic zero-knowledge proof schemes, and we're only solving this particular problem. And the property actually we're offering is witness indistinguishability. But at the same time, because these schemes are used for these solutions, we compared against those. Finally, again, this is the full like snapshot here, and this is what you can find also in our repository. Happy to accept contributors here, and yeah, here it is. I mean, thank you for listening to me, and happy to answer on any questions.